Hello everyone. In this video we are going to introduce the notion of Taylor polynomials. Alright, so we're going to start by working through an example just to give an idea of what a Taylor polynomial is and what its goal is. So we're going to start with the function f of x equals e to the x, and basically our goal is to approximate this with polynomials. Right, so e to the x is exponential. It's most definitely not polynomial, but there are times when polynomials are very nice, and so we want to see if we can approximate this with polynomials and do a decent job. So we're going to focus on this point as the point where we want to make sure we're definitely accurate, right? So you're used to power series where we know at our center we're definitely accurate. It's going to be the same idea here because we're eventually going to leverage our way up from polynomials to the infinite analog and being series. So, right, f of 0 is equal to 1. Okay, so if I'm looking for a 0th degree polynomial, which I'll call p0 of x, that needs to match this, well, 0 degree means it's just constant, right? And so it'd just be y equals 1. So, okay, this is clearly a terrible approximation, but it's most definitely accurate at the point 0, 1. Okay, so what's my next step? So then we're looking for p1 of x, which is going to be linear, right? So that it simultaneously agrees at this point. And again, a linear approximation, we also want it to be accurate in terms of the slope, right? So here we want p1 of 0 equal to f of 0. And p1 prime of 0 equal to f prime of 0. So basically they share the point and they share the slope at that point. Okay, well what does p1 of x look like then? Well, if p1 of 0 is f of 0, which is 1, then that means the constant term is 1. And then we're left with our x term. So we have some ax, and we want the derivative at 0 to be also equal to 1, right? Because what do we know about e? That f prime, or in fact any derivative, right, our kth derivative of x is also e to the x, and so our kth derivative at 0 is always going to be 1. So here we want f prime is 1, so we want p1 prime, which in this case is a, to also be equal to 1. So what is this going to be? This is just 1 plus x, right? So we get the line of slope 1 through the point 0, 1. Okay, so this is a little bit better approximation, but it's still not great, right? All right, so then what can we do next? So next, we go up another degree, right? So you're looking for a quadratic. So 1 plus ax plus bx squared, say, where p2 of 0 is f of 0. p2 prime, so the slope is shared. p2 prime is f prime. And then we can add one more thing on top, right? We can ensure that concavity is also the same, or that the second derivative is the same at this point. So in this case, p2 prime of 0, well, what is p2 prime? It's going to be a, once we take the derivative, plus 2b times 0 in this case for the x left over. So this is going to be a. So again, a is 1. And if we take the second derivative, right, the a constant term goes away, and the 2bx becomes just 2b. And so we get 2b, and this should also be 1. Again, all the derivatives of e to the x are e to the x. And so b is equal to 1/2. Okay, and so our p2 of x is going to be 1 plus x squared over 2. All right, so basically we get this guy here. So the curvature seems to match for a little bit longer, but again, it gets inaccurate as we go to the left especially. So now let's go ahead and look at what we do when we add the cubic and quartic in here and just kind of see what happens by looking at Desmos. All right, so here is our picture from Desmos. So you can already see the three that we had before, right? So we've got the y equals 1 down here. We've got our linear guy 1 plus x, and we've got our quadratic 1 plus x squared over 2. So then in purple, you see the cubic, right? And so this guy is actually somewhat accurate So it matches at least up to the right. It has this right curvature. It's pretty good here. And then, of course, the issue is that it goes off to negative infinity to the left. And the same kind of thing happens with the quartic, right? So this is the closest one on the right as it follows here. It's really pretty accurate until we go over here, right? And then, of course, again, it's going to go off to positive infinity. And this, in general, is the issue, right? So when e to the x is going to infinity on the right side, that we can approximate with polynomials pretty well. On the left side, though, we have a horizontal asymptote. And polynomials are always going to go to either negative infinity or positive infinity as we go, as x approaches negative infinity. And so this is going to be the part that is harder to approximate, and we see that at play here. So for e to the x, we have basically seen the following pattern. So our nth degree polynomial, what we were doing, right? So we had 1 plus x plus x squared over 2, 1 plus x squared over 2 plus x cubed over 6. And then we added an x to the fourth over 24 term. After that, what are these? These are exactly the factorials, right? And so in general, for degree n, we're getting exactly the sum from k equals 0 up to n of x to the k over k factorial. Right? And so this is the Taylor polynomial for e to the x specifically. But how do we actually get this? What's the form in general? So for the Taylor polynomial of degree n centered at c for the function f of x, our polynomial of the nth degree, so we're going to again call that Pn of x, is going to be the sum from k equals 0 to n. Again, this is tracking the power of x on each term, of the kth derivative of f at your center times x minus the center to the k all over k factorial. So let's see that this was really what was going on with e to the x, right? So for f of x equals e to the x, well, the kth derivative of x is always e to the x, right? And so when we were centered at 0, well, all of these kth derivatives were 1. And so that's why we were getting 1 there. And so we were just getting x to the k over k factorial, right? Because c was 0. And so this exactly works there. And the idea in general, again, is that we're trying to make successively each of the derivatives match up with our function, right? So we start by agreeing at the point, then we want the slope to agree, the concavity, the third derivative, the fourth derivative, and so on at our center. And this leads to more accuracy for points close to the center. So now let's work through one more example. So let's look this time at f of x is, say, cosine of x. Okay, so then let's just do a few derivatives. So let's find P4 of x, okay? So we want to end up finding through the fourth derivative. So the 0th derivative, if you will, or the original function is cosine. F prime is negative sine. F double prime is negative cosine. F triple prime is sine. And then we're right back where we started with our fourth derivative at cosine, right? And here we'll also center at 0. Okay, so f of 0 is 1, right? F prime of 0 is 0 because sine of 0 is 0. F double prime of 0 is negative 1. F triple prime is again 0. And then we're back to 1 again for our fourth derivative, right? So when I'm looking at my Taylor polynomial, right, my P4 of x, I'm going to have, well, my f of 0 plus f prime of 0 times x, or x minus 0 in this case, plus f double prime of 0, x squared, all over 2 factorial, or 2, right? Then plus f triple prime, x cubed over 6, plus f to the fourth, or the fourth derivative, sorry, x to the fourth over 24, or 4 factorial. So let's actually plug these in here. Well, I get 1. My odd terms just go away, right? I have no terms of odd degree. And so The next one I have on tap is this is a minus x squared over 2, and then plus x to the fourth over 24. And then in general, right, your nth degree is going to have 0 for all of the odd degree terms. And then you'll just have the even degree terms as x to the k over k factorial with a minus 1 to the k, because we're switching sign every time because we're bouncing between positive cosine and negative cosine. All right, so for your only exercise, I want you to find the fourth degree Taylor polynomial for the natural log of x centered at x equals 1. And of course, the natural log of 0 doesn't exist, right? So we can't center at 0, so we will center here at 1. All right, thank you for watching.